Okay, let's picture this. The Wright brothers flyer. Mostly wood fabric.
Right, that's the classic image.
But get this. Even back then, they made the engine crankcase out of aluminum to save weight.
Ah, yeah. That little detail tells you so much, doesn't it? Materials were critical right from the get-go.
Totally. And those wooden wings, they had this triangulated structure, super strong, but it also turned out to be great for maneuverability and light, of course.
It's amazing how those early designs combined needs.
Exactly. So today, we're diving deep, not just into any old metal, but into aerospace alloys. These are the specialized materials, the really engineered stuff that lets us fly higher, faster, even get into space.
And what's really fascinating is how aerospace demands have constantly pushed material science forward. It's not just about being strong, is it?
No, not at all.
These alloys have to cope with incredible heat, immense stress, all while being, as light as possible.
That quest for lightness.
Yeah.
It has real-world impact.
Huge impact. I mean, think about it. Shave off just the 1,000 kilograms from a big airliner.
Yeah.
You're potentially cutting fuel consumption by like 1.1 to 1.5%. That adds up incredibly fast.
Wow. And then there's the safety aspect. That's non-negotiable.
Absolutely paramount. Those early disasters like the Comet airliners, the square windows.
Oh, right. The fatigue failures around the corners.
Exactly. Tragic, but they led directly to things like safe life and fail-safe design philosophies. Basically, building in redundancy and predicting material lifespan. It's fundamental now.
So our mission today is to kind of unpack the key materials making all this possible. Based on what we've looked at, we're hitting three main groups.
Correct.
First up, aluminum and magnesium alloys, sort of the workhorses for aircraft structure.
The backbone, really.
Then titanium alloys. These are interesting because they pop up in structures and engines.
That versatility is key.
And finally, superalloys, the champs for handling the crazy heat inside jet engines. We'll also touch on composites and coatings, too. Can't forget those.
Sounds like a good plan. It's a huge field.
It is.
Yeah.
So, let's dive in. Where do we start? Maybe with aluminum.
Let's do it. Aluminum alloys. What's really remarkable is just how long they've been dominant. They were some of the first metals used in planes.
Like with the Wrights.
Exactly. And they're still the most common material in aircraft structures today, decades later.
And it wasn't just luck, right? As planes got faster, needed better performance, especially during World War I.
Yeah, that was a big turning point. Wood shortages were a problem, and the performance demands just kept increasing.
So that pushed the development of these light alloys. Aluminum, magnesium, titanium.
Precisely. The big challenge was finding materials that were low-density light but still had the necessary structural properties. Strength, stiffness, durability.
Right. You need light, but not flimsy.
Definitely not flimsy. Now, when we talk about aluminum for structures, how it's made is important. Casting is used more these days, partly thanks to the car industry. But for the main aerospace structures, wrought products are still king.
Wrought. So that's metal shaped by force. Rolling, forging.
Exactly. Think sheets and plates for the fuselage skin, usually pretty thin, maybe 1 to 10 millimeters.
Okay.
But then wing covers, they take a lot more stress, so they can be much thicker, perhaps 25 to 50 millimeters.
Wow, that's chunky.
Yeah. And then you get into things like bulkheads, those internal walls, or the main wing spars. Those can be even thicker still.
Gotcha. And keeping track of all these different aluminums?
Yeah.
There's a system for that, right?
Yes. The International Alloy Designation System, IADS. Started back in 1970, helps standardize everything globally.
And then those letters, F, H, O, W, T, temper designations.
Right. They tell you about the alloy's processing history, how it got its final properties. The T tempers are really important in aerospace.
Why T?
T generally means it's been heat treated to a stable condition. And often there are numbers after the T, like T6 or T8, indicating specific treatments. Sometimes they even add extra work hardening after the heat treatment.
Okay, right, to make it even tougher. So this is where it gets really cool. How do they actually make aluminum alloys so strong? It's not just pure aluminum.
Not at all. A key technique, especially for the heat-treatable ones, is precipitation hardening.
Okay, break that down.
Imagine you mix in a bit of, say, copper with the aluminum. Then you heat it up, cool it down really precisely, and tiny, tiny particles start to form inside the aluminum grains.
Like little obstacles.
Exactly like microscopic roadblocks. They make it much harder for the layers of atoms in the metal to slide past each other. That's what gives it strength.
And these particles, They change over time.
They do. They go through different stages, these things called GP zones, then other structures, often labeled with Greek letters like theta prime, theta double prime. It's actually often the intermediate, sort of unstable structures that give the most strength.
Huh. So not necessarily the final, most stable form.
Often not, no. Like in a common alloy like 6063 that's aluminum with magnesium and silicon, you get these beta prime precipitates. They actually line themselves up in specific directions within the aluminum crystal lattice.
Why do they do that?
It's energetically favorable. It's like they fit better that way. And that alignment, even the shape of these tiny particles, is influenced by the surrounding aluminum structure. It's all very interconnected at the atomic level.
It really is material science at its finest.
Yeah.
But are there any, potential problems with aluminum? Any downsides?
Yeah, a couple of things to watch out for. One is hydrogen. Sometimes during rapid cooling with water called quenching,
Okay.
tiny bubbles of hydrogen gas can get trapped inside the metal. It happens because the hot aluminum can react with water, producing hydrogen. If it can't escape, you get these little internal blisters.
Not good.
Not good. Another issue is impurities. If the aluminum isn't pure enough, you can get small, brittle particles of unwanted compounds forming. These act like weak spots, stress concentrators. They can make the material more prone to cracking.
So purity is really key.
Very key, especially for critical aerospace parts.
Okay. Now, our sources mentioned some specific alloys. 7075, 2024. Those sound familiar.
Yes, very common. Often used for fuselage structures, wing components, usually in those heat-treated tempers like T6 or T8 for high strength.
And there was 2618 for higher temperatures.
Right, slightly better temperature resistance. And then there are the aluminum-lithium alloys.
Ah, lithium, that's all about saving weight, right?
Exactly. Adding lithium significantly reduces the density. And like we said, every bit of weight saved counts hugely for fuel efficiency and performance. That drive for lighter materials is relentless.
Absolutely. Which brings us nicely to magnesium alloys.
Perfect transition. Yes, magnesium. There's been a real resurgence of interest in magnesium since the 90s, roughly.
Why then?
Again, driven by that need for weight saving, fuel efficiency, environmental concerns, magnesium is even lighter than aluminum.
But I feel like I hear less about it. Is it harder to work with?
Historically, yes. Magnesium has a different crystal structure than aluminum, which makes it inherently less formable, less easy to bend and shape at room temperature.
So how do they use it?
Casting has traditionally been very common. Pouring the molten metal into molds, magnesium melts at a relatively low temperature, which helps.
Okay.
But there's been a lot of progress developing wrought magnesium alloys that are more ductile, easier to shape. Alloys like electron 21, electron 675, they're being looked at as potential replacements for some aluminum parts, maybe even some composites.
Interesting. And there's a geopolitical angle here too, isn't there? With production?
Yeah, the source material notes that China really dominates global magnesium production. Something like 80% of the world's supply since the early 90s when their economy really opened up.
That's a huge share. Must impact availability, cost.
Absolutely. Supply chain considerations are always part of the equation for manufacturers.
So when designing magnesium alloys, what are the principles? Is it like aluminum?
It's a bit different. With aluminum, we talked about those strengthening precipitates, but sometimes if they grow too much, strength can decrease. In magnesium, engineers often rely more on forming stable intermetallic phases, specific compounds formed between magnesium and the alloying elements.
Intermetallic phases.
Right. Which ones form depends on factors like the relative size of the atoms, their electrical properties, how many electrons they have to share. Basically, the principles summed up by the Hume-Rothery rules.
Okay.
This leads to different types of strengthening compounds, like ones with simple structures or more complex ones called Laves phases, or others like Mg2-Usai, which we also see in some aluminum alloys.
So specific alloys for specific jobs.
Exactly. The sources mention AZ91, that's a common one for die casting, and those electron alloys, again, as higher strength options.
And where do we actually see magnesium in planes or helicopters?
Things like gearbox housings, engine components. Our sources mention castings in the Boeing CH-47 Chinook helicopter, the Sikorsky UH-60 Blackhawk, and even parts in the Rolls-Royce Allison AE3007 engine. So definitely finding important niches.
Okay, interesting. Shall we move on to titanium?
Let's do it. Titanium and its alloys are a really fascinating group.
What makes them stand out?
their unique combination of properties. They're strong, relatively light, though not as light as aluminum or magnesium, but they have excellent corrosion resistance, and crucially, they retain their strength at much higher temperatures than the light alloys.
So that's why they bridge the gap between structures and engines.
Precisely. They can handle moderate heat that would weaken aluminum, but getting pure titanium, that's a bit involved, isn't it?
Yeah, the source mentioned the Kroll process.
Yeah.
Sounds industrial.
It is. Basically, you take titanium tetrachloride, which is derived from the ore, and you react it with molten magnesium metal in an inert atmosphere at very high temperatures. Think 700 to 900 degrees Celsius.
Magnesium again?
Yep, magnesium acts as the reducing agent, pulling the chlorine away and leaving you with titanium metal sponge. There was an older process, the Hunter process, using sodium.
But Kroll is better.
Generally considered more efficient and, frankly, safer. Handling molten sodium at those temperatures is, tricky.
I bet. Okay, so once you have titanium, you make alloys. And we hear about alpha and beta titanium. What's that about?
So pure titanium changes its crystal structure with temperature. At lower temperatures, it has a hexagonal, close-packed structure called the alpha phase.
Okay.
At higher temperatures, it switches to a body-centered cubic structure, the beta phase.
Right.
Now, when you add other elements, alloying elements, they tend to stabilize one phase or the other. Some elements, like aluminum, are alpha stabilizers. Others, like vanadium, molybdenum, iron, chromium, those are beta stabilizers.
So they make the beta phase stable at lower temperatures.
Exactly. They lower that transformation temperature. If you add enough of these beta stabilizers, you can actually keep the titanium in its beta structure all the way down to room temperature.
So you can have alpha alloys, beta alloys, or a mix.
Or a mix. That's
Yeah.
very common. Alpha-beta alloys, like the workhorse Ti6Al4V, 6% aluminum, 4% vanadium, are widely used. By carefully controlling the alloying elements and the heat treatment, you can precisely tailor the microstructure, the arrangement of alpha and beta phases inside the metal.
And that microstructure dictates the properties.
Absolutely. For example, with Ti6Al4V, different cooling rates after heating it into the beta or alpha-beta region give you different structures. Slow cooling might give you a coarser, layered structure.
Like Widmanstätten.
Exactly, that Widmanstätten structure, which can be good for resisting fatigue crack growth. Faster cooling followed by reheating might give you a finer, more interwoven basket weave structure, which often provides a good balance of strength, toughness, and fatigue resistance.
So heat treatment is critical.
Absolutely critical for titanium alloys.
And getting the initial metal really clean and uniform, the source mentioned VAR, vacuum arc remelting.
Yes, VAR is super important for high-quality titanium. You basically take the raw titanium sponge, mix it with alloying elements, and maybe scrap, press it into a big electrode.
Okay.
And then you melt that electrode using an electric arc inside a vacuum chamber. The molten metal drips down and resolidifies in a water-cooled copper crucible.
Why the vacuum?
It pulls out dissolved gases like hydrogen and nitrogen, which can make titanium brittle. VAR also gives very controlled solidification, which minimizes segregation, meaning the alloying elements stay evenly distributed, and leads to a much more uniform, high-integrity ingot. They usually remelt it 2 or 3 times.
Right, for maximum purity and consistency.
Exactly. There are other melting methods too, like electron beam, cold hearth remelting, EBCHR, but VAR is very common.
And then shaping it. Forging.
Forging is the most common way to shape titanium parts. Hammering or pressing the ingot into the desired shape, usually at elevated temperatures. You can forge it in the alpha-beta temperature range, or for some alloys entirely in the beta range, although beta forging needs really tight process control.
Gotcha. And are we seeing newer, more advanced titanium alloys coming through?
Definitely. There's a lot of work on beta titanium alloys, which can offer even higher strength than the traditional alpha-beta ones. Things like Ti15Mo, Beta C, used where you need maximum strength to weight. And then there are titanium aluminides, TL. These are intermetallic compounds, lighter than the nickel alloys they can replace.
So good for engine parts.
Exactly, especially for things like low-pressure turbine blades. Using TL there can save significant weight, which means better fuel efficiency. There's even research into making single-crystal TL.
Single crystal, like the superalloys we'll get to.
Same principle, eliminating grain boundaries for maximum high-temperature strength and creak resistance. It's cutting-edge stuff.
Wow. And outside the engine, where else does titanium pop up?
All over, really. In commercial jets, you find it in landing gear components, engine nacelles, various fittings and brackets, even things like brake torque tubes. Also, its excellent corrosion resistance and predictable behavior make it great for things like high-pressure hydraulic systems or fuel tanks.
Fuel tanks. Better than composites.
Well, one advantage mentioned is inspectability. It's generally easier and more reliable to do non-destructive testing on a metal tank to look for flaws compared to a composite one. So pros and cons to each.
Makes sense. Okay, so we've covered the light alloys, the versatile titanium. Now it's time to turn up the heat, right? Superalloys.
Absolutely. Now we're getting into the really high temperature realm. Superalloys are the undisputed champions here.
They make up the biggest percentage of materials in a jet engine.
By weight, yes. Because they're used in the hottest, most demanding sections, the combustor, the turbine, parts where aluminum and even titanium alloys just couldn't survive. And their use isn't limited to aerospace. They pop up in power generation turbines, chemical processing, anywhere you need strength at extreme temperatures.
Just how extreme are we talking inside a modern jet engine?
We're talking temperatures potentially exceeding 1,500 degrees Celsius in the hottest parts. Combined with high pressures and corrosive gases from combustion, it's an incredibly harsh environment.
And even advanced titanium alloys or those intermetallics like TL just can't cut it there.
For the very hottest sections, no. Nickel-based superalloys, especially the advanced single-crystal ones like SRR99 or CMSX4, offer superior creep resistance at those temperatures. The source material uses the Larson-Miller parameter to compare them. It's a way to relate temperature, stress, and time to failure.
Are there materials that can handle even higher temperatures?
Yes, refractory metals like niobium, molybdenum, tungsten, rhenium, they have incredibly high melting points.
What?
But they're also very dense, heavy, and can be prone to oxidation. So while they have potential, their weight is a major drawback for aerospace applications. Nickel superalloys still hit that sweet spot.
Okay, so let's break down the superalloys. Our source mentions cobalt-based ones.
Yes, cobalt-based superalloys have a long history. Cobalt itself was studied early on for magnetic uses. Geographically, a lot of cobalt comes from the Copper Belt in Africa.
And what goes into a cobalt superalloy?
You typically add chromium for oxidation and corrosion resistance. Then elements like tungsten, molybdenum, tantalum, niobium are added. Often they form hard carbide particles, which adds strength. Carbon is key for forming those carbides. Aluminum and titanium might also be added to form other strengthening phases.
Carbides. Those are like the roadblocks we talked about in aluminum.
Similar idea, yes. Very hard, stable particles that impede dislocation movement. They form during solidification and heat treatment, and their exact composition can even evolve a bit during service life.
Interesting. Then there are iron-based superalloys.
Right. The source suggests they're maybe not the focus of as much cutting-edge research right now compared to nickel or cobalt, but they are still incredibly important and widely used.
Where do we find them?
In gas turbines, they're used for components that maybe don't see the absolute peak temperatures, but still need good strength and durability. Think compressor discs, some turbine discs and blades, casings, exhaust parts. They're generally processed in wrought form, forged or rolled for better grain structure control.
And their advantages.
A big one is cost effectiveness. Iron is obviously much cheaper than nickel or cobalt. And they still offer a really good combination of mechanical properties, creep resistance, wear resistance, and corrosion resistance up to moderate temperatures.
Okay. But the real stars of the show, especially for the hottest parts, are the nickel-based superalloys.
Without a doubt. They offer the best overall combination of high temperature strength, whether that's resisting sudden loads, slow creep deformation, or fatigue from cyclic loads, plus excellent resistance to oxidation and hot corrosion.
And these are complex beasts, aren't they?
Incredibly complex. The alloy design involves balancing maybe a dozen different elements, each playing a specific role. And the microstructures are highly engineered. You mentioned single crystal turbine blades earlier.
Yeah.
Think about that. A single complex-shaped component made from one continuous metal crystal operating at temperatures maybe up to 85% or more of its actual melting point. It's phenomenal engineering.
How do they achieve that? Casting.
Yes, casting is key for the most advanced blades and vanes. While some simpler nickel superalloy parts can be forged, wrought, the highest temperature components rely on investment casting, often combined with techniques like directional solidification, DS, or single crystal SC casting.
Okay, let's unpack the strengthening mechanisms in these nickel alloys.
Yeah.
What makes them so strong when they're almost melting?
It's a multi-pronged approach. First, you have solid solution strengthening, just like in other alloys, adding elements like Tungsten, molybdenum, rhenium to the nickel matrix makes it inherently harder for atoms to slide past each other.
Okay.
Then, like the cobalt alloys, they utilize carbide precipitation. Different types of carbides can form, like MC, M23C6, M6C, adding strength, particularly at grain boundaries.
Grain boundaries, they're important too.
Very important, especially for creep resistance. Small additions of elements like boron and zirconium segregate to the grain boundaries and strengthen them, making it harder for grains to slide past each other at high temperatures.
But the really unique thing is the gamma prime phase, right?
That's the star player, yes. Gamma prime, or GAS. These are tiny, ordered precipitates, usually based on the composition N3Al or Ni3Al-T. They have a crystal structure, L12, that fits almost perfectly within the main nickel matrix structure, FCC, called gamma, or Ga.
Coherent interface.
Exactly, a coherent or semi-coherent interface, which is very stable. These gamma prime particles are incredibly effective at blocking dislocation movement, especially at high temperatures. There's also another related phase, gamma double prime, found in some alloys containing niobium, which has a slightly different but related structure and also provides potent strengthening.
And doesn't the strength actually increase with temperature sometimes?
Yes, that's a fascinating aspect of gamma prime, the Kuhr-Wilsdorf lock mechanism. Up to a certain temperature, the way dislocations have to move around and through the ordered gamma prime structure actually makes it harder to deform, so strength can increase.
Yeah.
It's counterintuitive but crucial.
But eventually, if it gets too hot or the particles grow too big,
Then strength starts to drop off. If the gamma prime particles coarsen too much, that's overaging dislocations, find it easier to just loop around them instead of cutting through, a process called Orwin bowing. So controlling the size and spacing of gamma prime is critical.
and in the most advanced alloys.
They often have such a high volume fraction of gamma prime that the gamma matrix exists only as narrow channels between the precipitates. Deformation, especially creep, is then largely confined to these channels.
Incredible control. And the processing methods reflect that. Directional solidification.
Exactly. Directional solidification, or DS, is a casting technique where they control the cooling very carefully so the molten metal solidifies progressively from one end. This encourages the grains to grow as long columns, all aligned roughly parallel to the main stress axis of the part, like a turbine blade.
Why is that good?
It eliminates most of the grain boundaries that run perpendicular to the stress axis. Those transverse boundaries are weak links for creep at high temperatures. So DS parts have much better creep resistance than conventionally cast parts with random grain orientations.
And single crystal is the next step.
It's the ultimate step in that direction. Single crystal, or SC, casting uses a special pigtail or spiral structure in the mold base that acts as a grain selector. As solidification starts, multiple grains form, but only one is oriented correctly to grow up through the selector and form the entire component.
Sometimes they use a seed crystal.
Yes, they can place a small seed crystal with the desired orientation at the bottom to ensure the final part has that specific crystal alignment relative to the blade's geometry. By completely eliminating grain boundaries, SC casting provides the absolute best creep resistance.
But does this perfect solidification cause any issues? Segregation.
Yes, that's a factor. As the metal solidifies, some alloying elements prefer to stay in the liquid, while others prefer the solid. This partitioning leads to variations in composition on a microscopic scale, microsegregation. It can create slightly different properties in different areas.
Can you fix it with heat treatment?
You can try homogenization heat treatments, holding the part at a very high temperature to allow atoms to diffuse and even things out. But diffusion is slow in solids, especially in these large-grained DSSC parts, so it's often not fully effective.
And the regular heat treatment for these alloys?
Yeah.
Also complex.
Oh, yes. Very precise, multi-step processes are needed to get the optimal gamma prime precipitation. Typically, it involves a solutioning step heating high enough to dissolve most of the existing gamma prime back into the matrix, followed by quenching, or rapid cooling.
Okay.
Then comes one or more aging steps, holding at specific lower temperatures for controlled times. This allows the gamma prime to reprecipitate as a very fine, uniform dispersion, which gives them maximum strengthening. Some alloys, like Udamet 700 mentioned in the source, might have 2 different solutioning steps and 2 aging steps. It's a carefully choreographed thermal dance.
Wow. So even with these incredible superalloys, they still need protection inside the engine. That leads us to coatings.
Absolutely essential. Even the best superalloy will degrade relatively quickly in the extreme environment of a turbine's hot section without protective coatings.
What are they protecting against?
A nasty combination. Extreme temperatures, oxidation from the hot air, corrosion from impurities in the fuel or air, like sulfur, salts, erosion from tiny particles, and of course the mechanical stresses the parts are under. The specific conditions, temperature, pressure, gas speed, chemistry, loads dictate the type of coating needed.
And how do they put these coatings on? Our source mentioned thermal spraying.
Thermal spray is a big category. Techniques like plasma spray, HVOF, high-velocity oxyfuel, they all basically involve melting a feedstock material, powder or wire, and spraying the molten or semi-molten droplets at high speed onto the part surface where they flatten out and solidify to build up the coating.
How does this take?
It can be a combination of mechanical interlocking with the surface roughness, some diffusion bonding at the interface, and sometimes chemical reactions.
And vapor deposition.
Right, PVD, physical vapor deposition, and CVD, chemical vapor deposition. These are more about depositing the coating material atom by atom, or molecule by molecule, from a vapor phase onto the surface. They can produce very dense, uniform coatings.
There was also pack cementation for aluminum coatings.
Yes, tack cementation, particularly aluminizing, is an older but still used diffusion process. You basically bury the parts in a powder mixture containing aluminum powder, an activator, like a halide salt, and an inert filler. Then you heat it all up.
And aluminum diffuses into the surface.
Exactly. It forms aluminum-rich intermetallic layers, primarily nickel aluminide anneal on nickel superalloys, which are excellent at forming a protective aluminum oxide scale.
But it had issues with hollow blades.
Right. The pack process didn't reliably coat the internal cooling passages of hollow turbine blades. That led to the development of out-of-contact methods, like using slurries or gas phase processes, vacuum pulse, forced flow, to deposit the aluminum more uniformly inside and out.
Okay, so what are the main types of coating systems used?
Broadly, you have coatings primarily for resisting high-temperature corrosion and oxidation, and then thermal barrier coatings.
Let's start with the corrosion-resistant ones, aluminase and MCRALX.
Right. The basic idea for both is to create a surface layer that can form a stable, slow-growing, protective aluminum oxide, alumina Al2O3, scale when exposed to high temperatures. This is called selective oxidation.
So the coating acts as a reservoir of aluminum.
Precisely. Diffusion aluminide coatings, formed by processes like pack cementation, essentially convert the surface of the superalloy into Niel phases. They work well, but can be somewhat brittle.
And MEOALX?
MCLX coatings are overlay coatings, meaning they're deposited on top with a distinct composition, not formed by diffusion with the base metal as much. M is typically nickel, Ni, cobalt, Co, or a combination, Nico. Car is chromium for corrosion resistance. Al is aluminum for that alumina scale formation. And X represents a small amount of a reactive element like yttrium, Y, or hafnium, HF.
What does the yttrium do?
It dramatically improves the adherence of that protective alumina scale to the coating, preventing it from spalling off during temperature changes. M-SCIR L-elect coatings are generally more ductile than simple aluminides and offer more flexibility in tailoring the composition for specific needs. They are often applied by thermal spray or PVD.
Do these coatings interact with the superalloy underneath?
Yes, there's always some interdiffusion over time at temperature. A zone called the SRZ, superalloy reinforcement zone, can sometimes form. Failure of diffusion coatings can happen in several ways. The protective oxide scale grows too thick and cracks. That SRZ forms and maybe degrades properties. The aluminum in the coating gets used up. Brittle phases might form. Or the surface can even develop wrinkles called rumpling.
Okay, now thermal barrier coatings, TDCs. They sound important.
Hugely important for engine efficiency. TBCs allow engines to run hotter, increasing the turbine entry temperature, or TET without melting the metal parts. They act as thermal insulators. They're typically a two-layer system, a metallic bond coat, often an MCRALX type, applied first to the superalloy part for adhesion and oxidation protection.
Right.
And then a ceramic top coat applied over that, usually yttria-stabilized zirconia, YSC. Zirconia has very low thermal conductivity, so it keeps the heat out, allowing the metal underneath to stay cooler.
But they can fail too.
Oh, yes. Common failure modes involve the interface between the bond coat and the alumina scale that grows on it, called the thermally grown oxide, or TGO. If that interface weakens or the TGO grows too thick or wrinkles, the ceramic top coat can spall off. They can also be damaged by erosion, impacts from debris, foreign object damage, FOD, or attack by molten deposits, hot corrosion.
Got it. And the last type mentioned, Abrasive and abradable coatings.
These are used for clearance control in rotating machinery,
Right.
like between the tips of turbine or compressor blades and the engine casing.
To keep the gap really tight.
Exactly. Tight clearances mean less air leakage, which improves efficiency. Abradable coatings are applied to the stationary part, the casing. They're designed to be soft enough that if a blade tip rubs against them, the coating wears away preferentially without damaging the blade tip, essentially allowing the blade to machine its own path.
Okay.
Abrasive coatings can be put on the blade tips themselves. These are hard enough to cut into a compatible seal material on the casing. Examples of abradables include nickel graphite, graphite particles in nickel, or nickel bentonite, a clay mineral in a metallic matrix. The choice depends on what the rotating part is made of. You need careful matching. You wouldn't use bentonite against titanium, for instance. It's too abrasive.
Fascinating.
Yeah.
Such specialized materials for specific jobs.
Okay.
Okay, we've covered the big three alloy groups and coatings, but the source mentions some other interesting, maybe more niche or future materials.
Yes. The drive for higher temperatures and better performance never stops. This pushes research into areas like refractory metal alloys, oxide dispersion strengthened ODS alloys, and intermetallic compounds. And then there are materials with unique functionalities like shape memory alloys, SMAs.
Okay, ODS alloys. What's the idea there?
Oxide dispersion strengthening. You take a metal matrix, often a nickel-based superalloy composition, and you disperse extremely fine, stable oxide particles like yttria, Y2O3, throughout it.
How does that help?
These tiny oxide particles are incredibly stable at high temperatures and act as very effective barriers to dislocation movement, especially for creep. They essentially pin the dislocations. This gives ODS alloys excellent strength and creep resistance at temperatures very close to their melting point, sometimes even better than conventionally strengthened superalloys in certain regimes. Alloys like MA754, PM2000 are examples. There's even work on ODS molybdenum alloys.
And intermetallics.
Yeah.
We touched on TL.
Right. Intermetallics are ordered compounds formed between two or more metals. They often have attractive properties like high melting points, low density, and good oxidation resistance, but they can also be brittle at lower temperatures, which has been a challenge. Nalal, nickel aluminide, is a prime candidate studied as a potential replacement for some nickel superalloys because it's lighter and has better thermal conductivity.
How are they making them?
Research looks at casting them as single crystals or directionally solidified parts, similar to superalloys. There's also work on creating in situ composites, like eutectic alloys where two phases solidify together, for example, nalamo, or strengthening nalal with other precipitates. Iron aluminides Fiel are another class being investigated. Powder metallurgy is also explored as a way to get around some processing difficulties.
Lots of potential, but maybe some hurdles still.
Definitely. Brittleness and processing challenges are often key hurdles for intermetallics.
Okay, lastly, shape memory alloys. SMAs. These sound cool.
They really are. SMAs have this remarkable ability to remember a previous shape. You can deform them quite significantly in their low temperature state, and then when you heat them above a certain transition temperature, they'll spring back to their original predefined shape. That's the shape memory effect, SME.
How on earth does that work?
It's based on a reversible phase transformation in the crystal structure. They switch between a higher temperature phase called austenite and a lower temperature phase called martensite. The deformation in the martensite phase happens by rearranging specific crystallographic variants, twinning, detwinning, which is a reversible process when it transforms back to austenite upon heating.
And they could do other tricks too. Superelasticity.
Right. At a temperature slightly above the austenite finish temperature, they can exhibit superelasticity. You can stretch or bend them quite a lot, and they'll snap right back to their original shape when you release the load, like a super rubber band.
And where would you use something like that in aerospace?
Actuators are a big area because they can generate force and movement just by being heated. They can replace heavier, more complex motors or mechanisms, especially useful in space applications for things like deploying solar panels or antennas. The source mentions the Frangibolt system by Teeny Aerospace.
Vanderbilt.
Yeah, it's basically a fastener made of an SMA, often nickel titanium nitty or nitinol, that holds something in place. When you heat it electrically, it changes shape or length, releasing the mechanism. It's a very reliable, low-shock way to deploy things in satellites, often replacing older pyrotechnic bolts. Weight saving and reliability are key advantages.
That is genuinely clever engineering.
Wow!
Okay, we've covered a massive amount of ground here. from the Wright brothers aluminum crankcase to single crystal superalloys and sheet memory actuators.
It's an incredible range, isn't it? Each
Yeah.
material class optimized for its specific demanding role, whether it's the main structure, the blazing hot core of an engine, or providing a specific function.
It really drives home how fundamental materials science is to everything that flies.
Absolutely. And stepping back, you see this constant theme. The relentless push for better performance, higher efficiency, lighter weight, and above all, safety. That's what drives the continuous evolution of these aerospace alloys.
Yeah. Thinking back on our deep dive, a few things really stand out for me. That little detail about the FlyRise engine, it really foreshadowed everything.
It did.
And that direct link between weight and fuel burn, that 1,000 kilogram saving over 1% fuel, it just puts the importance of lightweighting into perspective.
Makes it very tangible.
And honestly, just the sheer complexity inside those superalloys, the gamma prime, the directional solidification, it's mind-boggling what's happening at the microscopic level.
It truly is materials design at an extraordinary level.
So for you listening, hopefully this gives you a deeper appreciation for the stuff that makes flight and space travel possible. It's not just aerodynamics and engines. The materials are just as critical.
And that brings us to a final thought, maybe something to ponder. Looking ahead, what's next for aerospace alloys? What breakthroughs might revolutionize air and space travel in the decades to come?
Yeah, like, could we see materials that actually heal themselves if they get damaged?
Or composites that are orders of magnitude lighter and stronger than today's? Maybe entirely new classes of alloys based on principles we haven't even fully grasped yet.
What are the big roadblocks, the fundamental material limits we still need to smash through to really push the boundaries of what's possible in aerospace?
That's the multi-billion-dollar question, isn't it? Something to keep an eye on as the field continues to evolve.